So the next section is going back to our rectilinear motion that we looked at back in Chapter 4 with derivatives. Now we're going to look at it with our antiderivatives. So remember when we talked about if we have a particle in rectilinear motion and we have a position function s of t, then its instantaneous velocity and acceleration are given by v of t is equal to the first derivative, so our velocity is equal to the first derivative of the position function, and our acceleration function is equal to the derivative of the velocity function, which, remember, is the second derivative of our position function. So then it would follow the formulas that s of t is an antiderivative of v of t and v of t is an antiderivative of a of t. That is that you can find the position function by integrating your velocity function, and you can find your velocity function by integrating your acceleration function. So for example, suppose that you have a particle that moves along the s-axis. They want to use the given information to find the position of the particle. So we want to find our s of t. So then what we're going to do is we're going to, given the velocity function in part A, now this is the initial condition, so this goes back to that initial value problem. We're going to have to use this information, this initial position. So at time t is equal to 0, the position of the particle is -3. We will use this information to solve for c, because now we're looking at the indefinite integral again. So s of t then is going to be equal to my integral of v of t dt. So s of t is equal to my integral of 1 plus sine of t dt. So then when I integrate s of t, well, I know the antiderivative of 1 is just t. The integral of sine of t is going to be my negative cosine t plus my c. So now to solve for c, what I'm going to do is I'm going to take -3, set it equal to, and plug in 0 for t, 0 plus negative cosine of 0 plus c. So -3 is going to be equal to 0, and then cosine of 0 is 1, so that's going to be -1 plus c. So c is equal to -2. So then my position function then is going to be, again, take my c and plug it back in. It's going to be equal to t minus cosine of t minus 2. So that's how, when you're given your velocity function, you can find your position function. Now in part B, notice they're not giving you the velocity function, they're giving you the acceleration function. So notice they're giving you two conditions. They're telling you that v of 1 is equal to 0, s of 1 is equal to 2. So to get to the position function given acceleration, you first have to find the velocity function. So the velocity function is going to be equal to the integral of, I'm going to rewrite 1 over t squared as t to the -2 dt. So when I integrate v of t, again, adding 1 to -2, that's going to give me a t to the -1st, divide by -1, so that's negative t to the -1st plus c. So then v of t is going to be equal to -1 over t plus c. So now I'm going to use this initial condition, v of 1 is equal to 0, to help me solve for c. So I'm going to let 0 be equal to -1 over 1 plus c. So c is equal to 1. So then my velocity function, v of t, is equal to -1 over t plus 1. So then to find my position function, s of t is going to be equal to the antiderivative of -1 over t plus 1 dt. So when I integrate, well, I know the integral of -1 over t is going to be negative natural log of the absolute value of t. Integral of dt is just going to be plus t plus c. So now I'll use the initial condition where they're telling me that s of 1 is equal to 2, plug 1 in for t, and then let s of t be equal to 2. So 2 is equal to the negative natural log of 1 plus 1 plus c. Well, natural log of 1 is 0, so 2 is equal to 1 plus c. C is equal to 1. So then my position function then is going to be equal to the negative ln of the absolute value of t plus 1. that's how you can integrate to help you find your position function, whether you're given velocity or acceleration. So now going back to displacement and total distance traveled. Again, the displacement, t over a time interval, is the final coordinate minus its initial coordinate. Thus, if the position of the particle is s of t, then its displacement or change in position over time interval. Again, to find your displacement, what you can do is you can integrate your velocity function or integrate the first derivative of the position function. And then again, using your fundamental theorem of calculus, you can plug in your upper bound and your lower bound. Displacement is a vector. It has a length and a direction. In contrast, remember to find your distance traveled. It's the distance traveled in the positive direction plus the distance traveled in the negative direction. You must integrate the absolute value of the velocity function. That is, again, to find your total distance traveled. It's going to be equal to your time at t sub 0, t sub 1, and it's the absolute value of your velocity function. So remember, going back to when we talked about total area, we will have to take this region that's falling below the x-axis and take the absolute value and have it reflect in order to calculate the total distance traveled.